Hi all, welcome back to another round of astronomy. So I've got some questions for you. We'll start off with this one just to kind of get your brain going again. Which star cluster is older? Go ahead, take a minute, examine these two pictures, get an idea. Good. Now, don't forget, the answer is important, but why you have that answer, justification is even more important. Now, I'm not going to give you the answer yet because I have a second question that presents information in a slightly different manner. Okay? So this one is visual. You can actually get it visually from this, and I'll backtrack after we talk about the next slide. Here's another question for you. Same idea. Two HR diagrams of star clusters. Which one's older? Go ahead, take a minute, figure it out. You got it? I hope so. Good. And notice I've swapped the order, right? So you got to be careful. This order is different than this order. Okay? So let's go ahead and talk about the HR diagram for a moment, and then we'll go back and see visually how that's portrayed. So you notice right away in the HR diagram, we have this diagonal line going from upper left to lower right. And that line is what we would call the main sequence. And that main sequence just goes through all of the different stars all the way through. And I apologize. Boy, I'm missing an O there. Let me add that in. Magic. Now over here in star cluster B, you notice we start off with the lower right and we start going up, and then all of a sudden we have this gap here, right? This main sequence doesn't seem to keep going. And the question I have for you is, where were those stars? The stars that would be here, the A-type stars, the B-type stars, where did they go? And hopefully you came up with, those stars have burned out. They have gone through their fuel, and they're no longer found on the main sequence. They are no longer performing hydrogen-hydrogen core fusion. Rather, they have started evolving off the main sequence. That's why you have this branch here. What you're seeing in this branch are stars that used to be on the main sequence. They have run out of hydrogen fuel in the core, and now they're making their way up towards the helium flash and later the asymptotic branch. Okay. So the question then becomes, which star cluster has been around longer? And we say the cluster that no longer has the B-type stars, the A-type stars. Let's go back and look. What does that look like visually? Well, here's the question for you. A B-type star, roughly what color is it going to be? Blue, right? B-type stars are really hot. B-type, O-type stars are really hot. They should be more bluish in color. This M68 star cluster doesn't have any blue stars in it. That means it must be the older cluster. It's been around long enough that the blue type stars that used to be in here have burned out. They've gone into their red giant phases, or maybe they're in their asymptotic branch phases, or maybe they're already white dwarfs. So we know based on the color that this star cluster is younger than this one. We have a term for this. I've highlighted it here, but we call this location the main sequence turnoff. Okay? It's the point where stars on the main sequence have started burning out, turning off of the main sequence to become red giants or red supergiants. And based on that, we can actually estimate the age of the star cluster. You want another shot at it? Here we go. Go ahead. Here's another star cluster. It's M55, I believe. Go ahead. Tell me, how old, roughly speaking, is M55? Take a minute. Go. Here's another infographic, and it's just giving you the relative size of the various star types. It's giving you roughly the coloring, if you will. But the thing that we really need right here, and I'll highlight for you, is the temperature. Boom. Highlight. Good. So the issue that we need here, let's take the HR diagram, we see the main sequence right here. And this is real data, right? You want to look up the paper, it's right here. Okay. And here we go. So we go along the main sequence, and right about here, we notice that those stars have turned off. So what we need to do is we need to estimate, according to this graph, the temperature where that turnoff point is located. I'll draw on the line for you right here. Okay, so each of these hash marks is about 200 Kelvin. So I would estimate that we're roughly at about 6,500 Kelvin. So now we go to our chart. Which temperature? 40,000. Excuse me, there's a missing zero there. 40,000, 20,000, 8,500, about 6,500. We notice that that corresponds to the F-type stars. So let's say 6,500 F-type stars. That's where the turnoff point is. So let's see, what's the lifetime of an F-type star? About 3 billion years. So based on where this turnoff point is, because our F-type stars are no longer there, they're basically burned out, we can estimate that the age of this cluster is about 3 billion years. Here's the analogy. Imagine you have a candle and you have different layers of the candle. Say they're different colors. You have the M layer and the K and the G and the F and the A and the B and the O. Okay? And when your star cluster forms, that's like having the full candle. And right when it forms, you light the candle. And depending on how long you wait, you know that that candle is going to get smaller and smaller and smaller. So the size of the candle, if you will, indicates how long it's been burning for. Okay. Good. Let's keep moving here. So after 20 minutes of review and getting really excited here, let's get on to the main topic for today's lecture. We are now going to start tackling what I call the distance ladder. Okay. We are going to start progressively measuring further and further into space. How do we do that? We've started out with our first measurement being parallax, painter's thumb. We stick our thumb out at arm's length. We see it jump back and forth due to the the difference in position of our eyes. Because of that, when we hold our thumb out and swap, we alter the viewing angle ever so slightly, and we can use that slight shift to estimate how far away our thumb is. We do that also in the solar system or beyond. We called that the parallax method, and that is the first method for estimating distances to stars. Remember, we use that, and knowing the distance to stars, about 150 million of them, we were able to construct the first HR diagram. Now we are at a position where we need to think about how can we use the HR diagram to measure even farther in space. So that's the first set of things that we're going to walk through today. Okay? So right now we're out to about, say, 500 or maybe 500 parsecs. That's about 1,500 light years. Okay? Just ballpark. That's how far we've been able to measure so far. Let's get an idea about how to go further. So this next method is either referred to as main sequence fitting, and I personally prefer that term, but sometimes you'll also see it written as spectroscopic parallax. Okay. We're going to walk through how do we actually perform this. Okay. So the first thing I need to point out to you is how to actually get a distance. Okay. And I'll go back to the equation that I gave you, I think it was in the magnitudes chapter. I said, hey, we use this to compare brightnesses of two stars. So I'll go ahead and put that up. Okay? And unfortunately, remember, we use little m to refer to the apparent magnitude. Now, here's something that I'm going to do. Okay? Instead of comparing two stars, star 1 and star 2, I'm going to look at the same star. But I want to view that star from two different distances. Okay. One being the distance from the star to the Earth. That would give us the apparent magnitude. The second distance I want to consider is the distance from that star to 10 parsecs. And when we look at a star from a distance of 10 parsecs, we call that the absolute brightness or the absolute magnitude. So I'm going to use this equation, but I'm going to think about comparing the star as seen from its current position to the star seen from a distance of 10 parsecs. So let me put that up. And you notice I've changed two things. Instead of calling it star 1 and star 2, I have now used the absolute brightness and the apparent brightness. So absolute ABS and apparent APP. And also, instead of saying the apparent brightness of the two stars, the apparent magnitude of the two stars, I am now using the apparent magnitude and the absolute magnitude. Good so far? Okay. Here's the next thing. And we're walking through. I want to get this equation so that I can get an idea about distances. Okay, so keep in mind, we want to find an equation that gives us distance as related to the apparent and the absolute magnitude. Okay, that's where I'm going. Here's the next thing. I'm going to use our equation for brightness. We have an equation that relates brightness to luminosity. I'll put it up here. This is the rich uncle problem. Okay, so that's even further back in the chapter where we were discussing information that we can infer from light. So I'll go ahead and put this equation up. We said that the brightness of an object, and right here I was thinking the apparent brightness, is the luminosity of the star divided by 4 pi r squared. Remember that 4 pi r squared is the surface area of a sphere that's centered around that star. And then r would be the radius of that sphere. Okay. Follow me so far? It's not a QL for nothing, right? Now here's the next thing. This is why I'm walking you through it. I didn't just want to hand you the equation, although you probably have already seen it. What we're going to do next is I'm going to take the equation that we have for brightness and luminosity, and I'm going to go and plug it in to this equation up here. Now keep in mind, for the absolute magnitude, I'm viewing it from a distance of 10 parsecs. So let's go ahead and put that in. Now it's going to look messy. It's a compound fraction. We'll simplify it in a second. Okay. So that's all I've done here. I've taken the L divided by 4 pi r squared and put it in the numerator. Now notice instead of using r, I've used 10. Why have I used 10? Because the absolute brightness is as viewed from 10 parsecs. So right here, when I put this 10 in, keep in mind that now I'm dealing in parsecs. Okay? Notice in the bottom, I've just done the luminosity divided by 4 pi r squared. Okay? Now let's get rid of that compound fraction. I hate compound fractions. Let's get rid of them. This L divided by 4 pi, you notice I have it in the numerator, L divided by 4 pi. I have in the denominator, L divided by 4 pi. I can just cancel those out. Right? And if I want to get rid of the compound fraction, I can just write it like this. I have now r squared divided by 10 squared equals, and I haven't changed anything on the right-hand side here. Now we're home free, right? Let's multiply both sides of this equation by 100. And notice if I multiply this side by 10 squared, right? And the left side gets multiplied by 10 squared. The right side gets multiplied by 10 squared. And so I can just write that as the original and then plus 2, right? I can, if I multiply 10 to some exponent by 10 to another exponent, I can just add the exponents. I'm going to take the square root of both sides. I could take the square root of both sides. But when I take the square root, that's like saying r squared, and then the square root is like taking the exponent and dividing by 2. That's a different way that we can write the square root. So what I can do here is I'll divide 0.4 by 2. I still have little m minus big M. And then I divide 2 by 2, so I get this plus 1. Okay? So at the end of the day, let's go ahead and get rid of all of this. At the end of the day, what do I have? I have this. So these two equations are synonymous. It's just a matter of what information are you given. Are you given the brightness and the luminosity? This would be a better bet. Are you given the magnitude and the absolute magnitude? Then this would be your better bet. Good so far? Okay. So now let's start getting into the nitty-gritty details. We want to figure out how can we use the HR diagram to start estimating distances to stars. So here's one for you. Let's say for a moment you have the apparent magnitude of a K05 star. Okay. Now, how do we get the apparent magnitude? We go outside, we set up our telescope, and see the apparent magnitude, the apparent brightness of the star. Okay, so that one, we never talk about how to get the apparent magnitude or the apparent brightness, because that's an issue of setting up your telescope, making the data collection from Earth. That is the easiest piece of information to get. Okay? Here's the question for you. The apparent magnitude of a K05 star is 3.5. How far away is the star from Earth? And notice I've put in parsecs. Okay? Don't forget that the result of the past slide, the answer is in parsecs. The distance is in parsecs. Go ahead, take a minute, hack it out. Good? Awesome. Now, it's not by accident I've given you this HR diagram, because you need to use the HR diagram in order to solve this problem. So let's start off with this. A K0 star. That's the spectral class, right? Any Cannon. So we need to go down here and say, okay, well, we've got the O's, the B's, the F's, the G's, the K. Oh, the K's. There we are. There's the K's. And then the question is 0. Is that on the cold side or the warm side? That's the warm side. K0 would be right here, for example. Okay. A K9 would be right here on this side, and then an M0 would be right there. So K0 is between, if you will, the G and the K. Now you see already how we actually use the chart. The fact that it's a 5, now that Roman numeral gives us the luminosity class. A 5, Roman numeral 5, luminosity class corresponds to the main sequence. Okay? It's very important. Anytime you want to do main sequence fitting, excuse me, I almost fell into the other term here. Anytime you want to do a main sequence fitting, you have to use a main sequence star. Okay? So we have a main sequence star. That's what we have indicated by this 5. So we go down to our HR diagram, we find where the K0 is, and we see where that intersects the main sequence. Then we put in our horizontal line and see where it intersects the vertical axis. What are we doing? We are getting an estimation of the star's absolute magnitude. Here I've chosen something like 6.5. You might have read something slightly different. That's okay. You've got the right process. Now we have everything that we need. We're given the apparent magnitude, 3.5. We've used the HR diagram to find the absolute magnitude, 6.5. Now we just need to plug in our numbers, 3.5 and 6.5. Sweet. And then we run our numbers. Okay. So we have a difference of 3. Don't forget the negative sign, very important, right? 3.5 minus 6.5. So we have a negative 3 in there, very important. And so we run this in our calculator. So we get negative 0.6 plus 1. So that should be 10 to the 0.4. We turn the crank and, oh yeah, by the way, we already happen to know 10 to the 0.4, right? That's 2.5. So this star, this K05 star, which has an apparent magnitude of 3.5 and an absolute magnitude of 6.5, that star is a distance of about 2.5 parsecs away. Okay. Now notice what we did. You had to use the spectral class of the star and the HR diagram to estimate the absolute magnitude, or correspondingly, the luminosity of the star. You see it? Let me review it for you. This is how main sequence fitting works. Okay? We take the spectral class, we make sure that we have a luminosity class of 5, a main sequence star, and we use those to estimate the absolute magnitude or the luminosity of that star. In other words, okay, we are now using the HR diagram as the model. Let me take a step back. Remember that we used the parallax method to determine the distance to about 150 million stars. That's what formed our forest. Based on those distance measurements, we were then able to use the distance to those stars and the apparent brightness to find the luminosity of that 150 million stars and create our first HR diagram. Now, here's the magic part. We are going to assume that the HR diagram is accurate, in other words, displays the birth, life, and death of stars that are further away than 500 parsecs. In other words, we assume that the pattern that we observe for nearby stars also applies to stars that we can't measure the distance to directly. That's a big jump, right? We are going to take the HR diagram and assume it applies to stars further away that we can't measure the distance to directly. Okay? That's where we're using the HR diagram as our model now, assuming that it applies to more distant stars. And if it applies to more distant stars, then we can use the spectral class of that star and the HR diagram to get the luminosity. Pretty cool, huh? And that allows us to then estimate the distance to those stars. So by this main sequence fitting technique, we can now go even further in our galaxy. Something like from 500 parsecs to, say, 300,000 parsecs, almost 1 million light years. You say, well, what's the limit there? Why can't we go further than 1 million light years? Here's the deal. The star has to be bright enough so that you can get a reasonable spectra. And you know that if as a star gets further and further away, it appears dimmer and dimmer and dimmer. Okay. If it gets too far away, it will be so dim that we can't even get a reasonable spectra out of it. We can't identify where the absorption lines are. And if we can't identify where the absorption lines are, we can't say what class of star it is. We can't identify its spectral class anymore. And if we can't identify its spectral class, then we can't use this main sequence fitting. Even for the brightest stars, the O-type stars, the B-type stars. Those stars, once they get out to about 1 million light years, they're too dim for us to be able to identify their spectral class. We have to do something else. You say, well, that's not a big deal. Main sequence stars, 1 million light years, that's fine. Keep in mind, the distance to the next galaxy, the next closest galaxy, is about 2.5 million light years. That's M31, the Andromeda galaxy. It's 2.5 million light years. We can't do main sequence fitting to estimate the distance to the Andromeda galaxy. We need something else. We need a better method. I shouldn't say a better. We need a method that will allow us to measure even further into space. Good so far? I'm going to shut down right here just to give us a nice break. Go ahead, take a breather, come back and see the next method. Thanks for your attention. I'll see you soon.